Okay, so this is the unit on ocean acidification, and I want to start here because in science we have to deal with things like this. That somebody will publish an article or a paper that says, well, ocean acidification is a hoax. And I want to point out a few things here about what the author is saying. So the author says, however, the oceans are not an acid. They never have been in geological history and cannot become an acid in the future. And I agree with this author. Changes in atmospheric CO2 cannot produce an acid ocean. I also agree with the author. Marine life depends on CO2. I agree with the author. Some plants and animals fix it as limestone. I agree with the author. So even though I've agreed with all these things, why am I going to talk about ocean acidification then if I'm agreeing with a bunch of stuff from an article titled The Hoax of Ocean Acidification? A lot of it has to do with how the author presents the information, and more importantly, what the author is leaving out. So let's get into it. So first off, what is ocean acidification? It's the ocean becoming more acidic. A different way of looking at it, and I think this is the problem with the name, is that the ocean is becoming less basic. And this is a problem that we've had with names in the past, like global warming. Now we call it climate change because some people will look at an area and be like, well, it's cold this year, what happened to global warming? Well, we're looking at the average temperature of the planet overall. So we had to change the title so that we'd have less problems. Ocean acidification has run into this problem. Everybody thinks that, oh, that means the ocean's going to become an acid. Am I going to burn my face off? Is my skin going to melt out? Not even close. Another one that we're going to encounter later on is something called the Great Pacific Garbage Patch, and that is another name issue that we're going to have to deal with. So let's look into some of the basic causes of ocean acidification. Basically, it's carbon dioxide. It is often referred to as climate change's twin brother or twin sister. It's the other side of the coin. Carbon dioxide, because we're producing so much more by burning fossil fuels, almost 11 billion tons of this stuff, we are running into problems. First off, too much CO2 in the air is a greenhouse gas, and it's trapping more heat on the planet. So overall, not in every little location, but overall, the planet's temperature is rising. CO2 naturally dissolves into water and the ocean. Like even in my fish tank, CO2 is naturally dissolving there. The thing with CO2 is we actually need it for photosynthesis to occur. And that's why I go back to this article here. The article says CO2 is important. Yeah. But what the author doesn't tell you is that too much CO2 or too little CO2 is dangerous. You need to have basically the right amount. If you have too little, photosynthesis won't happen. If you have too much, well, that's what we're looking at now. Ocean acidification begins to happen. So the ocean, it depends on who you ask, is absorbing anywhere between 25 to 50% of all the carbon in the atmosphere. It's more likely around 30%. But even in any case, it's more than it should be holding right now. So this should be something that is kind of sketched in your notebook, and we can take a look at, okay, in the 1750s, it was just above 275 parts per million. That's what the ppm means. But now we're climbing up pretty high. In 2019, we are hitting above the 400 parts per million mark. Like in this old graph, we only had it up to 400 parts per million. We have now exceeded that. It's gone off this particular graph. And so NOAA, National Oceanic Atmospheric Administration, monitors all this. And every year, we just see the trend climbing. And like I said, right around 2019 is when we passed the 400 parts per million mark. We have not seen that in human history, in human time. As long as humans have been around, it has never been that high ever. Has it been that high in the past? Yeah. But this is when no humans were around and there was a lot of volcanic activity. Is there volcanic activity now? Yeah. As much as there was before? No. So where's all this CO2 coming from? Well, from the fossil fuels that we burn. Have our predictions always been right? So again, this is something where they will come after scientists for and say, well, your predictions aren't right. A better way to look at this is we feel that there's a trend happening, that the amount of CO2 is going up year after year after year. So if you look at like 2015 to 2016 to 2017, 2018, we see a gradual climb in the amount of carbon dioxide in the atmosphere. And in 2018, we like if you look here at the red peak, that's where we predicted it was going to be at. It was a little bit lower. Instantly, people started saying, aha, see, your projections are wrong. Not really. It's still climbing. That's what we've been saying the whole time. So while carbon in the atmosphere is bad, it causes its own problems with climate change. We're focused on the ocean. And to really understand it, you got to keep track of the hydrogen ion. And that might not mean anything to you right now, but we're going to get into this. In the most basic terms, pH, which is a measure of hydrogen, and it only measures hydrogen, it's basically a balance between hydrogen and something called hydroxide. The OH you don't even really need to worry about. pH ranges from 0 to 14, 0 being very acidic, 14 being basic. It doesn't mean that basic is safe. They're like opposite ends of a temperature scale. Too hot is dangerous, too cold is dangerous. 7 is right in the middle. It's neutral, and that's typically pure water. The lower the number, the higher the acidity. So something like 0 is acidic, again, 7 is neutral, 14 is basic. I kind of look at it like this. Look, the more hydrogens you have, think about it like a scale, like a teeter-totter. If I start putting more hydrogens, well, it's going to lean this way. More hydrogens is more acidic. Okay, so it's getting you closer to 0. Imagine 14, like 0 being on the floor, 14 being up here. If you start taking hydrogens out, so less hydrogen, it starts getting lighter compared to the OH, in which case it gets closer to 14. Pure water, like if you broke up so here's the two H's and the O, if you broke it up, it's the perfect balance between hydrogens and hydroxides. Okay, like I said, the hardest part here is to switch your brain to say, look, more hydrogens, lower pH. It's like an indirect relationship here, so just be careful with that. So what about like household items? What are their pHs like? Like, okay, is a 3 really dangerous? Well, you probably have a pH 3 at least once a week. Anytime you drink a soda, you're drinking something about a pH of 3 when you use vinegar in your salad dressing or like lemonade, you're probably drinking something around a 2. And no, it doesn't burn your throat off or whatever. But you can taste the difference. Like it has like this sour taste. This is what I mean by like the whole safe thing. Like 13 and 14 are like oven cleaners and bleach. Like that is not safe for your skin. So being at 14, like I said, is not an indication of being safer than 0. Like I said, there are opposite ends of the spectrum. So what does that have to do with the pH of seawater? Well, the pH of seawater before the 1800s was above 8.2. Currently, it's 8.1 or around 8.1. And, people are thinking, well, what's the big deal? It's still not an acid because, again, I go back to this and an acid would have to be lower than 7. Like, well, see, ocean acidification, it's a base. It's still a base. Yeah, but if you look at 8.2 to 8.1, it is getting more acidic. It's dropping this way. That's what they mean by ocean acidification. It is getting closer to 0. It doesn't mean that it's going to be at 0. Now, if we look at our predictions, and again, our predictions, like, are they spot on all the time? Like this? No, but the trend that we're predicting is happening. We're estimating that by 2100, it's going to be below 7.5. The question is, going back to the article, this one, okay, is 7.5 going to be an acid? And the answer is no. No, it's not. It's still technically a base. But what the author doesn't tell you is that, look, it used to be above 8.2. Now it's at 8.1. We're on the march to 7.5. It is getting more acidic. We never said that it is going to be an acid. We just said it's getting more acidic. And that's because our pH is dropping closer to 0. Doesn't mean it's going to be at 0. So how do we know? And at this, so at 7.5 and lower, the shells begin to dissolve. Right now, shellfish can still form their shells. It's just getting a lot harder. And again, we'll talk about this in a second. So how do we know what the pH of the ocean was way back when? Or how do we know how much CO2 was in the atmosphere? Like, does anybody have any old jars of air just sitting around? Not really. It's in ice cores. And, we're going to watch an ice core video in class, but that explains how we extract old air. So what does that have to do with the oceans? Well, calcifiers. So a calcifier is anything that uses calcium and carbonate to create their shells. Anything that has calcium carbonate, clams, oysters, lobsters, coral, these two down at the bottom are pretty important. One's called a pteropod, phytoplankton. We'll definitely get to talking about those more in detail later on. For right now, I just kind of want you to include them. These are all things that have shells on them. So this is a pteropod shell, and they put it in water that was 7.5, and over time it becomes deformed because it is harder and harder for the pteropod to form its shell. There's less available material. So now the question becomes, why? So in your equation box is, a bunch of equation boxes, you have like this huge grid explaining all this. So I'm going to go to the animation here, and this kind of explains ocean acidification. So here we have carbon dioxide and water. Carbon dioxide is kind of the culprit of everything that's happening. And when carbon dioxide comes into contact with water, it will form H2CO3, which is carbonic acid. Now, carbonic acid is kind of unstable. Again, we're not in a chem class, so we're not going to get into the details of why, but almost instantly, and if I brought in the soda stream to class, I injected carbon dioxide into water. This formed, but almost immediately, boom, hydrogen pops off of this thing. Okay, and it creates something called bicarbonate, which is H, so here's the H, C, here's the C, and then O3, 1, 2, 3, and a loose hydrogen ion. Now remember what I said about pH. pH is a measure of, loose hydrogens. So the more loose hydrogens you have, the more the pH is going to drop. So in this animation, the pH just dropped because now you have a loose hydrogen. So the interesting part is this loose hydrogen is actually going to attach on to carbonate. Now if I come back to this diagram here, carbonate is floating in water. So is calcium. This is not a shell yet. These are like separate in the water. Okay, but calcifiers can take this one and this one, combine it to make their shells. But what happens is, after this carbonic acid, what I just showed you in the animation, it pops off the hydrogen, which I showed you in the animation. Here's bicarbonate. Shellfish can't use it. This hydrogen is actually going to attach onto this CO3 minus, the carbonate, and it's going to become more bicarbonate. Again, I know there's a lot of words and whatnot, but just if you're in class over the last week or so, you should have been putting this together. So you create more bicarbonate. All right. So what does that mean? Well, the calcifiers, they need this. If they don't have carbonate because the hydrogen keeps stealing it, they're going to have a harder time making this. I use the example like it's like making hot dogs. If you have 500 hot dogs but only 5 buns, you can't make 500 hot dogs. You can only make 5. So same thing with the shells. It doesn't matter how much calcium you have. If this is running out, you're having a harder time forming shells. And that's exactly what's happening in the ocean. The other thing is, what happens if there is no carbonate, but there's shells? Well, the hydrogen is going to come over and it's going to knock the calcium off to become bicarbonate. Now, what happens here is your shell, calcium carbonate, CaCO3, is actually dissolving. Like this is when it gets really bad. When there's no more carbonate in the water and the hydrogen begins to break your shell apart. And that won't happen unless it's very like it's under 7.5, under 7.5. Then you'll start seeing that happen. So the big idea is like right here. Like this is where like the meat of your notes is at. If you can understand what's going on here, you get a good grasp of what's happening with ocean acidification. Now, what are we saying in terms of the U.S.? Well, the U.S. produces the second highest amount of carbon dioxide, with China being the largest producer of carbon dioxide. India comes in like third, and then everybody's like 5% or lower. If you combine every other country other than these right here, they make up about 19%. But that, like I said, that's every other country other than listed here. So us and China are like the two main contributors. As far as impacts on the U.S., the West Coast is being impacted more than the East Coast. That has to do with the temperature of the water. Don't need to know that, but do know that like us on the West Coast are feeling the impacts way more than the East Coast is. In particular, two industries right now. The oyster industry is having trouble, and the salmon industry. And I know I talked about like calcifiers being things with shells, and you're like, well, salmon don't have shells. You're right. But they are affected by pH because they're having a harder time smelling, and they need their sense of smell to get back to their spawning location. And then the other one is oysters. In Washington, they're having a big problem with water that is more acidic, and oysters they can form the shells. It's just so much harder for them to do it. They're having a hard time getting full grown anymore. And these are just some other areas that are being affected because of ocean acidification. Just remember, like, the more carbon dioxide you have, the lower the pH is going to get. This has to do with like carbonic acid and popping off the loose hydrogens. And that's really about it. The big thing for this unit is, like I said, making sure you understand this part really, really well, and your critical thinking questions, which there's a separate video for that somewhere.